Time for some practice for problems which involve limits and infinity, and also some asymptote problems. Now, as always, you should try to do as much of these problems as you can on your own before seeing the solutions. The more you can do on your own, the better you're going to get. And it does get better. The first 1,000 problems are always the hardest. And then they get a little bit easier. No, it doesn't take 1,000 problems, but it does take work. All right, so make frequent use of that pause button. Try to do as much as you can, and only once you get to a point where you're stuck, really stuck, then use it to help get you unstuck. Or maybe once you have a solution, you can review it to see perhaps a different perspective. The more that you do, the better that you're going to be. All right, let's get started. So find the limit as x approaches 1 of 3x squared minus 7x plus 5 divided by x cubed minus 2x squared plus x. All right, now notice this limit is not a one-sided limit. So we have to understand the behavior from both directions. All right, does that mean we're going to take two one-sided limits? No, it just means we got to be careful. So first off, let's think about what's happening. So we should always start by plugging in our point here and see what happens. So let's plug in 1. When you plug in 1, what do you get? Well, you get 3 minus 7 plus 5. 3 and 5 make 8. Subtract 7 makes 1. Downstairs, 1 minus 2 plus 1. That's 0. So goes to 1 over 0. All right, now when you see a number over 0, it means something's blowing up. But of course, it could blow up in a couple of different ways, and then we have to know. Now, what's going to happen? If they both blow up in the same way, say this would be positive infinity, this would be negative infinity, then we say the limit exists, either positive infinity or negative infinity. But if they have different behaviors from the two different sides, then it's going to be no limit. The limit doesn't exist because it's not approaching the same value. So what we need to do is focus on the signs. What's the sign on either side? Now, the good news is that the sign upstairs is always going to be positive. So we can say, look, the upstairs, because it's close to 1, and it turns out 1 is a positive number, so the upstairs is positive. So really, our goal right now is to get a handle on what's it doing downstairs. If we understand the downstairs, then we'll know the sign. So we know when we plugged in 1, we got 0. So that says it should factor. So let's work on factoring this. So we have x, and I see I can factor an x out. So let me just start by doing that. X squared minus 2x plus 1. Now, x squared minus 2x plus 1 has to be a root. So I should be able to find a way to write this where one of the factors is x minus 1. What's the other factor going to be? Well, if I pull out x minus 1, it'll be x minus 1. Well, x squared minus 2x plus 1 is actually a perfect square. So our denominator looks like what? The downstairs. Well, the downstairs looks like x times x minus 1 squared. Now, let's think about what's happening near 1. So, near 1, the x is positive because I'm near 1. Around 1 is a positive value. X minus 1, by itself, it depends whether we're below 1 or whether we're above 1. But, you see that square? Regardless of whether I'm above or below, I'm going to end up being positive because of the squaring. So, this is also going to be positive, which means, lo and behold, it's not just that it's 0. What's happening is it's going to 0 in some sense in a positive way. That's what we really need to dig into. We're asking the question, it's 0, but how do I get to 0? Is it in a positive or a negative way? And so we can say, look, when we're getting close to 0, well, that's not the upstairs, it's the downstairs. My goodness. So the downstairs is also positive. And therefore, the result is I'm taking a positive 1 over a very tiny number that means I'm blowing up positive on both sides. Therefore, this limit is infinity. And we're done. So the limit does exist. I'm going to do something like that. All right, good. That one wasn't so bad. Ha ha ha. Hopefully the rest are also pleasant and enjoyable. Well, of course they will be. Come on. It's math. Gotta have some fun. Ah, my goodness. Look at all these variations where we're having sine of something over something. Okay. Find the limit as t goes to 0 of 1 over t sine of 1 over t. Now, it says from both directions. I will note that 1 over t times sine of 1 over t, it's actually an even function. So if you know how it's behaving on one side, it's going to mirror it on the other side. So we might just draw one side and be okay with it. Now, our first sort of natural inclination is to say, hey, isn't this like sine x over x? And isn't that going to be 1? Well, let's be careful. So this can also be written as sine of 1 over t over t. And that's true, because that 1 over t becomes just a t downstairs. But now, what do? Well, what you do is you do a comparison. Does 1 over t match with t? And the answer is they do not match. And why is that important? Well, that means that we're not in a sine x over x situation. Something else is happening. So let's take a second to think about our two pieces. We have ourselves a 1 over t and a sine of 1 over t. Now, let's talk about sine 1 over t, because we've talked about this before. So sine of 1 over t does what? Well, what it does is this has this sort of infinite oscillation, so that as you get closer and closer to 0, it oscillates more and more frequently and tries to oscillate infinitely often right next to 0. And of course, it does something similar on the other side. Okay, so that's what the sine of 1 over t is. Oh my goodness, I've drawn in so many oscillations you can't even see the axes anymore. Okay, let's throw in some axes there. All right, so what happens then with the 1 over t? Well, 1 over t does what? So 1 over t, it does this. Ah, I'm getting ahead of myself. Shh. Pretend like you didn't see that. All right. You're going to, all right. 1 over t. There we go. So that's what 1 over t looks like. What happens when we multiply? Well, here's actually the nice thing about that sign. See, sine normally oscillates between -1 and +1. So when I multiply sine times something, what will happen is it'll oscillate between 1 times that something and -1 times that something. So in other words, if I have this function, it's going to oscillate between those pieces. So what happens? So 1 over t sine t, what we do is we come in, we sketch ourselves 1 over t, and we sketch ourselves -1 over t. So what we want to do now is we want to oscillate, go back and forth between these two. So, but we're still going to do a lot of oscillation. So what's happening? Well, what happens is we oscillate more and more, and can you see what our behavior is? So as I'm coming into 0, what am I approaching? Well, this particular function is trying to be very, very generous and saying, look, I don't want to limit myself. I don't want to approach just one value. I'm going to approach all the values. See, look at it. It's going farther and farther up and down. As I get closer to 0, it oscillates more, but not only does it oscillate more, it also oscillates higher and higher. By symmetry, it's going to do the exact same exact same thing on the other side. So I'm not going to sketch that, but I can see now I'm definitely not approaching a single value, And as soon as I know I don't approach a single value, that's enough for me to make the conclusion that this limit does not exist. All right, so there we go. A limit does not exist. Good. Okay. Now, let's try another problem. Find the limit as x goes towards infinity for e to the x plus e to the 2x sine of 3e to the negative x. Divide that by 3e to the x plus 5 plus 7e to the negative x. Okay, cool. Now, what do we do? Well, let's think about what's happening here. What's happening upstairs? Well, the e to the x gets big. E to the 2x gets really big. It's like, well, we're going to get into this, but make a little note here. E to the 2x is really big. How big is it? It's the same as e to the x squared. This is one of the things we often do with e to something x. We're like, oh, it's a secret in disguise. It's like e to the x to the something. But the point is that e to the 2x is getting pretty huge. And sine of 3e to the minus x. Well, now things are getting interesting. So here we have e to the minus x is getting small. So the inside is getting a very small value. So sine of a small thing is very small. So I have a huge thing times a small thing. That's a little bit less clear right now. We're not going to commit to what that is. But it's certainly going to be positive. And we already have a big thing. So, okay, so the top is getting huge. The bottom, the 3e to the x gets big. 5 is always 5. Not that big by most standards. And the 7e to the negative x, well, that's going to get small. So, big over big. So our conclusion here, this is going to infinity over infinity, which, no surprise to us, means we need to do a little bit more work. Now, what's our more work going to be? One question to ask is, what's the rate of growth? Okay, that seems like a good question, because when you have infinity over infinity, you're like, slow it down, slow it down. We need you to come in to something nice and finite. And right now you're not. You need to slow down. But how do we get it to slow down? We need to understand how fast it's growing. Now, when you look at the top, you say, well, I see e to the x and I see e to the 2x. E to the 2x feels bigger because it is bigger. But you gotta be careful. This is one of those times when it almost might mislead you. Even though e to the 2x is bigger, it is being pulled down by something. So it's a little bit ambiguous about which one of these two is bigger growth right now. But downstairs, it's a lot clearer to see. You see the e to the x is the only thing getting big. The 5 doesn't change, and the e to the minus x gets small. So I say, okay, so my growth that I'm going to try to use to get cancellation is the e to the x. If I cancel out that growth, then I'll be good. Okay, so that's where we're going. So, idea. We're going to start with our limit here. 4 e to the x plus e to the 2x sine of 3e to the minus x. Divide that by 3e to the x plus 5 plus 7e to the minus x. And then we're going to divide out by our growth. 1 over e to the x, 1 over e to the x. And when I say divide out by our growth from the downstairs. We just need to pick one of the upstairs to the downstairs. We pick whichever one is more convenient. All right, so we multiply this out. What do we get? Well, this is going to become the limit as x goes to infinity of 1 over e to the x times e to the x. Well, that'll cancel out. So 4 plus, here, 1 over e to the x, e to the 2x is e to the x. And then you have sine of 3e to the minus x. Downstairs, you get 3 plus 5 over e to the x. See, the e to the x is canceled off the 3, 5 over e to the x, and then you get 7. Now, e to the minus x is the same as 1 over e to the x, so there was already 1 over e to the x there. Now here's another one, so that actually gets to become e to the 2x. All right, so we're making progress. So good news, good news. Now, what do we know? Well, we spot some things. The 5e to the x goes to 0. 7 over e to the 2x goes to 0, so that's happy. 3 goes to 3. Great. 4 goes to 4. Wonderful. That says we know most of it. But we don't need to know most of it. We need to know all of it. How do we handle this piece? So let's come to the side. And we'll think about e to the x sine of 3e to the minus x. So what do we do? Well, what I want to do is I want to make whatever's on the inside match what's underneath it. So right now I see the 3e to the negative x is on the inside. So I want to put something underneath that looks like 3e to the negative x. For example, 3e to the negative x. All right. Well, if I put it downstairs, I have to compensate, and I'll put it upstairs as well. So let's see. What do we have? Well, what can we do? Well, one thing we can do is you have the e to the x here and the e to the minus x here. Those will cancel with each other. So they knock themselves out. So what's left? Well, you have the 3, and that's just 3. And now, notice what we have here. Sine of something over something. Perfect for what we want to do. Because these match, and they go to 0. So this piece goes to 1. So that last missing piece is going to go to 3. All right. So we put this all together, and we come to the conclusion that we get upstairs 4 plus 3, downstairs 3, also known as 7/3. Good. Done. Now let's pause for a second and think about some things we could have done. Now, once you get the hang of understanding growth, then you start to realize, hey, I can really make progress without having to do very much in this problem. So, as an example, let's look at what we have. Now, there's a couple of key things to remember. So we've mentioned this before, but of course, it doesn't hurt to mention things again. So, when I'll say theta is small, sine of theta is about theta. It's a good rule of thumb for very small values of theta. And we often care about small values of theta because we're taking limits of theta. Sine theta over theta goes to 1, which means sine theta over theta is about 1. So, if we were to parse this, we say, well, that looks like on the top 4e to the x. Then we have e to the 2x. And then it's multiplied by something where the inside is getting small. Well, so if it's sine of a small thing, it's approximately, I can replace that by the 3e to the small thing. Downstairs, what do I have? Well, the 3e to the x, but the 5 and the 7e to the minus x, by comparison, are small. In the long run, they're not significant. They're not going to contribute to the value. And so I'll ignore it. So right now, I'm giving you sort of the heuristic idea. What do you think of when you see these problems? And we look at them and say, well, upstairs, oh, this is really 4e to the x. And here the e to the 2x and e to the minus x become e to the x. So you get 7e to the x over 3e to the x, or 7/3. So there you go. So when you start to understand like what's important and what's not important, then you can start to say, oh, I see what the answer will be. We still need to do the work because we have to justify things. But once you have this ability to understand, hey, I know what matters, then you get a lot of power. And with great power comes great responsibility. All right, let's try another problem. Okay. Find all the asymptotes, all of them, for the function g of x is 2e to the 2x plus 3e to the x minus 5 over e to the 2x minus 4e to the x plus 3. Now notice it didn't specify vertical or horizontal, which means we've got to do both. So let's start with the horizontal. The horizontal is actually very straightforward in terms of what we need to do. We ask ourselves a question, what happens as we go towards our infinities. So let's say take the limit as x goes to plus infinity of our function to e to the 2x plus 3 e to the x minus 5 over e to the 2x minus 4 e to the x plus 3. What's causing our growth? Well, what's causing our growth is the largest factor. The constant doesn't do it. E to the x grows pretty big, but e to the 2x grows even bigger than e to the 2x. Sorry, e to the x grows much smaller than e to the 2x. So that's e to the 2x is our growth. So divide out by the growth. 1 over e to the 2x, 1 over e to the 2x. And what do you get? You get limit as you head to infinity of upstairs 2 plus 3 over e to the x minus 5 over e to the 2x. Downstairs, you get 1 minus 4 over e to the x, and then plus 3 over e to the 2x. And now we're like, hey, this is a good situation for us. We like where we're at because we're seeing pieces that are going to be small. That's going to be small. That's going to be small. This is going to be small. And this last piece is going to be small. So in other words, everything with an e to the x or an e to the 2x downstairs is going to be small. It's going to go to 0. And we're left with just the 2 and the 1. So it's 2. Now, if you've ever thought about it as taking limits of polynomials, one of the things that you sometimes learn is that if you take a limit as you head towards infinity and you have a polynomial over a polynomial, look at the leading coefficients. Assuming the degrees match. Okay, so first off, let's assume the degrees match. Then you divide out by the leading coefficients. It's the same philosophy. See, taking the leading coefficients and dividing out is really saying, let me look at what is important. What's causing the growth? And then you can say, all right, I'm going to divide out, and all that's left are the leading terms. Okay, good. Now, we're not done with horizontal. And we also need to take the limit as we go towards negative infinity of what? Well, same function, 2e to the 2x plus 3e to the x minus 5 over e to the 2x minus 4e to the x plus 3. But now we're in a much better situation. Because we're approaching a negative value, e to a negative number is going to get smaller and smaller. It's going down. So it's going to go towards 0. So now what doesn't go towards 0 is the terms on the end, the constant terms. So we're going to get 0 plus 0 minus 5, downstairs 0 minus 0 plus 3, or negative 5/3. And now we found the horizontal asymptotes. All right, cool. Halfway done, right? Now, where do we find the vertical? Well, for the vertical, we need to think about where are the vertical asymptotes? Where could they occur? So the vertical is look for denominator equals 0. See, the denominator equals 0, that would be where we have a divide by 0. So it's something divided by 0. And that means something is probably breaking, like an asymptote. Okay, so let's look at it. E to the 2x minus 4 e to the x plus 3 equals 0. Now, this is going to make us go, huh? How do you solve that? Well, here's a case where we say, hey, you know, e to the 2x, there's another way to think of e to the 2x. Namely, another way to think of it is e to the x squared. Aha, this is nice. It's one of these things that once you see it a couple times, you're like, okay, I know to look for. And if you can start to train yourself to look for, hey, quadratics are more common than you think. You just need to have something squared plus something times whatever plus a constant. You know, you're looking for that opportunity to arise. Okay, so since we have a quadratic, all right. So again, if you're not comfortable with working with e to the x, just give it a different name for the time being. Y equals e to the x. Then what this becomes is y squared minus 4y plus 3 equals 0. It's the same thing. It's just we've changed our names. Now, can we solve this? Yes. You're going to be, I don't know if I'll say surprised, but you're going to see that a lot of the problems we do involve polynomials that factor. You might leave this class thinking, wow, everything factors. It's not true. Not everything does factor. Sometimes it doesn't. So you have to do the work. So you do need to know the quadratic formula, but look for things to factor. Does this factor? It does. It does. Do you see what it factors as? Well, it factors as y minus 1 and y minus 3. I need to find two things that multiply by 3, multiply to get 3, and add together to get negative 4. Okay, which tells us that we need the y, which remember that's e to the x equals 1, or e to the x equals natural log of 3. Now that's what e to the x is. What is x? Well, x is log of 1, also known as 0, or x. Whoops, I got ahead of myself. X is 3, e to the x is 3, so x is log 3. There we go. I am so sorry about that. All right, well, I'm glad I corrected that mistake. You know, no matter how long you do math, you're going to keep making mistakes. So one of the things to do is to sort of like try to catch yourself, because you know it's going to happen. Think about your answers. Is that reasonable? It's like, wait a second, hold on. There shouldn't be a log yet. That's still coming. You don't want to get too far ahead of yourself because, well, that's when mistakes happen. Okay, we're not done yet, by the way. We're not done yet. Take a look. Look closely. Something is happening here. Is it the case that 0 and log 3 are vertical asymptotes? Can we say that definitively right now? And why not? What needs to happen? Okay, so in order for them to be vertical asymptotes, we really need to be dividing by 0, but the top also can't be 0. If it was a 0 over 0, it doesn't necessarily mean vertical asymptote. It means that there's more work to be done. So we cannot say we're done yet. So what do we need to do? Well, let's now look at the top. So let's do the same treatment to the top that we did to the bottom. So what did we do? Well, 2 e to the x squared plus 3 e to the x minus 5. Or, if you like, 2y squared plus 3y minus 5. Now, you might think, okay, well, do we have to factor? Well, actually, we don't have to do a quick check. Because what do we need to do? Well, remember, y is our e to the x, right? So the question is, if we plug in 1 or 3, do we get 0? When you plug in 1, you get 2 plus 3 minus 5. Oh, that is 0. Oops. Oh, my gosh. Oh, my gosh. Okay, hold on. Okay, well, that's actually good information. So we now know that 1 is a root here. So that tells us that y minus 1 is a factor. So a factor says y minus 1. Well, what's the other factor? Well, I need to get y times something to produce 2y squared. That's got to be 2y. And minus 1 times something to produce minus 5. That's going to be a plus 5. All right, so it really factors as e to the x minus 1 and 2 e to the x plus 5. So now we're like, oh, hey, that tells us that our original function hadn't been simplified as much as possible. Someone didn't finish simplifying when they gave it to us. So, because what do we mean? It means, look at the upstairs. It factors as e to the x minus 1, 2 e to the x plus 5. And downstairs, it factored as, see the y minus 1, y minus 3, that's e to the x minus 1 and e to the x minus 3. In fact, there's a simpler way to write this function. 2e to the x plus 5 over e to the x minus 3. So x equals 0 is out. That is not actually a vertical asymptote because it's a place where there was a cancellation. Now, to be fair, x equals 0 would be what we call a removable discontinuity. So there is a problem at 0 with the original form of the function, but it is not an asymptote problem. It's a removable discontinuity problem, which is a problem, but well, we have ways to solve it. So where are the vertical asymptotes? Well, log 3, because if you plug in log 3 upstairs, you're not going to get 0. So we have one vertical asymptote. By the way, I should have said that when you have horizontal asymptotes, we oftentimes write these in the form as, whoops, don't need to write over there, y equals 2 and y equals negative 5/3. So horizontal asymptotes are horizontal lines, which have the form y equals something. Vertical asymptotes are vertical lines, which have the form x equals something. So we have 2 horizontal, 1 vertical. All right, good. Well, if you like that type of problem, I've got some good news. We're going to do a similar type of problem to finish up. All right. So, find all the asymptotes for the function f of x, which is x squared plus 4x plus 3 over x squared minus 2, absolute value of x plus 1. Aha. Cool. Now, so we want to understand these. We want to understand what's going on. In fact, we really want to dig into it. And, first off, whenever you see something that involves an absolute value, our reaction will be like, ugh. Absolute values can be tricky to work with because they're a little bit harder to manipulate. So how do we get rid of absolute value? Well, the nice thing to do is to say, hey, I'm going to take your expression and I'm going to rewrite you in one of two ways, depending upon what the absolute value does. So for instance, when we're positive, the absolute value doesn't do anything. So this becomes x squared plus 4x plus 3 over x squared minus 2x plus 1. Now that's if we're positive. If we're negative, it does do something. It flips the sign. So it becomes x squared plus 4x plus 3. Downstairs it becomes x squared. It's minus already, and if we flip the sign, plus 2x plus 1. And that's if x is less than 0. All right. So now, in some sense, we get to do two functions, right? So we're going to have to deal with one function. Oh, by the way, I should have specified one of these should have been at 0. It doesn't really matter because the absolute value is equal at 0, either form, x or negative x. So let's tackle our various asymptotes. So the horizontal, that'll be probably the easier one. So we're going to take a look at the limit as x goes to infinity of our function. Now, as I'm going towards infinity, positive infinity, I look like the top because I'm going to positive infinity. I might as well only take big positive numbers. So I look like x squared plus 4x plus 3. Divide that by x squared minus 2x plus 1. All right, good. Now, what happens next? Well, it's going to get big upstairs, big downstairs. It's going to infinity over infinity. All right, everything's going towards infinity. So what do we need to do? We need to start slowing things down. What's the biggest term? What's causing the growth? It's the x squareds. So what we do is we divide out by the x squared. Now, you might be familiar with the idea of look at your leading coefficients. This is where the idea of leading coefficients comes from. Because what's happening is if you divide out by your leading coefficients, then you're going to slow everything down to the point where anything that's not a leading coefficient is going to go to 0. Because what happens is now these other pieces like the 4x and 3 are now going to be divided by x or by x squared or by whatever it is. They're going to be divided by powers of x, which means in the long run, they're going to get small. And therefore, we get 1 over 1, which is 1. Now, to be fair, you still have to do the limit as x goes to negative infinity, but now that you have this idea of leading coefficients implanted in you, It's a slightly different function because we're negative. It's the same process though. If you have a polynomial, same degree on top and bottom, look at the first leading coefficient at the top. In other words, the coefficient of the highest power. Look at the coefficient of the highest power downstairs. Take that ratio, because once you divide out by the growth, everything else goes to 0. So this will also equal 1. All right. So horizontal asymptotes, easy. Vertical. All right. Cool. So let's think about where could the vertical asymptotes be. So we've got to look here. Let's start with the first case. Now, we have x squared plus 4x plus 3. X squared minus 2x plus 1. What's another way to write x squared minus 2x plus 1? Well, it's a perfect square, so it can become x minus 1 squared. When does this equal 0? Well, it equals 0 at 1. That's easy to spot. Now, we pause before we go any further and say, okay, we have a problem at 1. Do I care? And the reason I ask, do I care, is does 1 fit into the region that I'm worried about? So I only care about values of x which are above 0. It turns out 1 is above 0, so it's like, okay, I got to pay attention. Now, we're going to be careful and cautious and ask, well, what happens when I plug 1 in upstairs? So when I plug in 1 upstairs, what do we get? Well, upstairs we'll get 1 plus 4 plus 3. So we say, aha, there's a problem at 1. But moreover, we can say the limit as x approaches 1 of our function x squared plus 4x plus 3 over x minus 1 squared. We see the top, it's going to a number like 8, in that it's going to 8, and the bottom it's getting small, but because of the square, it's going to be a small positive. Both directions, we're coming in from both sides. So this is a case where we're going to get infinity. All right, good. Now, this is the, should have made a note here, x greater than or equal to 0. What if, all right, we're going to put all that, I should mark, okay, x equals 1. We're going to put this all together in a nice picture in just a few minutes here. The last thing, x less than or equal to 0. Okay, so we have x squared plus 4x plus 3. Downstairs we get x squared plus 2x plus 1. Does that factor? Wow, it does. What are the odds? Pretty good. Pretty good, actually. So the factor is x plus 1 squared, which means there's a potential problem at negative 1. We quickly check. Yep, negative 1 is below 0. We definitely need to think about it. We don't know if it's an asymptote yet. We ask, okay, what happens when you plug negative 1 upstairs? Well, when you plug negative 1 upstairs, you'll get negative 1 squared, which is 1, minus 4 plus 3. Oh, my goodness. 1 minus 4 plus 3, that's 0. So we get 0 over 0. We need to do more work. All right, that means that there's something to do on the upstairs. Well, it really means that one of our factors is x plus 1. Well, if one factor is x plus 1, the other factor would have to be x plus 3, because I need to get the x squared, and I need to get the 3. Divide that by x plus 1 squared. Now we say, okay, really our function should have been x plus 3 over x plus 1. So this function up here is really x plus 3 over x plus 1. All right, now we say, okay, what happens? Well, as we take a limit as x goes to 1, it's a little bit, negative 1. It's a little bit different than what we had up here when we went towards 1, because we had that benefit of the square. This is not squared, which means it's not going to be the same sign from both sides. One side will have a positive side, one side will have a negative sign. So we've got to be careful. So let's be extra careful. So if we take the limit as x approaches negative 1 from below, well, what is true? That says we're a little bit below negative 1. So If we're below -1, we're a more negative number. So it's like -1 minus a little bit. So x plus 1 is negative. How about the upstairs? Well, it's like really something close to -1 plus 3, which is about 2 plus a little bit. So it's like 2. So it's 2 over a negative number. So that means it's going to be a very large negative number. So we go to -infinity. The limit, as we approach -1 from above, x plus 3 over x plus 1, what is that going to do? So now if I'm at -1, I'm a little bit above -1. So I'm a little bit larger. Okay, so that means that x plus 1 is positive. Positive number here, upstairs still about 2. So it's 2 over a very tiny number, which means we're going to be a huge positive number. So it's like infinity. All right, so now we really understand everything. So let's mark what's happening with our function. So there's a couple of things. We know we have an asymptote here. We have an asymptote at horizontal at 1. So here would be our horizontal asymptote. We'll write it as y equals 1. Oops, I'm off the screen. Here we go. Now we're back on. Y equals 1. And then we have vertical asymptotes at, say, -1 and at +1. Now, long-term behavior is what? In the long term, as we look at our inputs, so in other words, going left, right, we're always going to approach 1. So I'm going to head towards this dotted line here. Let's talk about now our behavior at -1. As we approach -1 from below, we're going to head towards -infinity. So that says we're going to head this way as we approach -1. So it's reasonable that our function should do something like that. As we approach -1 from above, so in other words, as we come in from above, we're going to go to +infinity. So we're going to be doing something like this. As we approach 1, and it doesn't matter which way we approach +infinity. So it's going to be doing something like that. Now, I don't know how far down it goes. So I could plot some points, but I'm not so worried. Now, finally, we're going to approach y equals 1 in the long run, so we're doing something like that. So that's roughly what our function would look like. Now, it's not exact. There could be a little bit of movement. One side note, I haven't mentioned this before, and you've been so patient. You came all the way to the end of this video. So I'm going to just throw out a little bit of a tidbit, just as a reminder. So oftentimes when people think about asymptote, they think about the idea as like, well, you're getting closer to it, but you never cross it. Vertical asymptotes, that's true. We're getting closer to it, but we don't cross it. It's not true with horizontal asymptotes. You are absolutely allowed to cross the horizontal asymptote. So what could happen, and I can't rule it out, because all I've done is a few asymptote computations. There's nothing that says that I can't come down and then come back up in the long run. And in fact, you can cross an asymptote infinitely often. So for instance, if you look at the function y equals sine of x over x, we see this function a lot, don't we? If you think about what happens in the long run, well, as x gets large, sine of x is never going to get big. It's always between -1 and 1. And then the denominator gets big. And so what happens is it's going to get smaller and smaller, but it's going to keep going above and below. So it actually crosses its asymptote infinitely often. Just a little tidbit, something to keep in mind. So while you're laying awake at night, it's like, oh yeah, I guess you can cross asymptotes a lot. That's true, isn't it? Good to know. All right. Well, thanks for hanging in there. Keep up the good work. See you later.